Thinking Aloud. Conversations on the leading edge of knowledge and discovery with psychologist Jeffrey Mishlove.
Hello, I'm Jeffrey Mishlove. Today, our topic is hyperspace, understanding hyperspace. This is once again going to be a Skype-based interview with my dear old friend, Saul-Paul Sirag, who is the author of ADEX Theory, How the ADE Coxeter Graphs Unify Mathematics and Physics. And he is also the author of an appendix published in the second edition of my book, The Roots of Consciousness, and the appendix is titled Consciousness, a Hyperspace View. Now, once again, I have to say that this interview is going to be rather technical. I've done two previous interviews with Saul-Paul, and I'm linking to them right now. One is on physics and consciousness. The other is on string theory, and you'll see the links in the upper right-hand corner of your screen. Those are hot links. If you click on them, they will take you right to those videos, and if you haven't already watched them, I think you'll get much more out of this video if you do that. And now I will switch over to the YouTube conversation. Welcome, Saul-Paul. It's good to see you once again. When we think of hyperspace, I'm reminded of the book by, I believe it's Abbott, Edwin Abbott, written, I think, over 100 years ago, called Flatland, in which he basically explains what hyperspace is like by imagining what it would be like for an entity, a person, so to speak, living on a plane rather than in a three-dimensional world.
Yes, that's a very popular book. It was widely read, especially early in the 20th century, and a lot of people got the first idea about hyperspace. Now, A. Abbott was actually some kind of minister, and his idea was to make people more comfortable with the idea of the spiritual realm, actually. In effect, suggesting that the spiritual realm may well be a realm that has more than three dimensions that we usually think of as spatial dimensions. And one of the things that he does in the book that's interesting is that the Flatlanders are entities in a two-dimensional space, but occasionally they see strange things happening, like a point appear in the space, and then a point gets bigger and bigger and bigger, and then it gets smaller and smaller and smaller and disappears. And of course, this would be, from our three-dimensional point of view, this would simply be what they would see if a sphere entered Flatland and went through Flatland. That's what the Flatlanders would see. They see this point.
The idea being that even though these Flatlanders are two-dimensional creatures, when they see each other, they really are only able to see across the plane, so they see one dimension.
That's correct, yeah.
And so the implication is, I would think the implication is if we see each other as three-dimensional creatures, we might actually, in fact, be 4 or 5 dimensional.
Yes, or higher. Mm-hmm. The interesting thing is that when Abbott's book came out, physicists weren't interested in the idea of hyperspace, but at least not until several decades into the 20th century. Interestingly enough, the first hyperspace version of reality that came out of physics actually happened in the 1920s, and that was an attempt to unify Einstein's theory of general relativity which, by the way, requires a four-dimensional space-time to be allowed to be curved. The curvature of space-time is what Einstein's theory says is what gravity is all about. So right after Einstein published that in 1915, other people thought that they might be able to bring electromagnetism into the same sort of picture. And two different people named Kaluza and Klein. One was a mathematician, one was a physicist. And in the 1920s, early 20s, they came up with the idea that if there was an extra dimension, in other words, if there was a fifth dimension to space-time, then actually Maxwell's theory of electromagnetism would be implicit in the theory. And Einstein himself helped Kaluza get his paper published, because Kaluza was a pretty totally unknown guy at the time. And Einstein himself wrote some papers on that, but he didn't like the idea of an extra dimension, so he worked on other attempts to unify electromagnetism with his theory of gravity. Now Klein was a physicist, and he dealt with the issue of, well, why don't we see the extra dimension, the fifth dimension? And he being a physicist brought in the quantum mechanics idea that, in other words, if you employed the fact that the Planck constant is the smallest thing possible according to quantum mechanics, that you could make the fifth dimension roughly that size, not much bigger. And so that helped to explain why we don't see the extra dimension. It's a tiny dimension, not much bigger than the Planck length, which is about 10 to the minus 33 centimeters, which is 20 orders of magnitude smaller than a proton. So a proton can't even move around in this extra fifth dimension of Kaluza and Klein. But then, this idea was totally forgotten about, basically for 50 years, partly because physicists were more excited about delving into the issue of other forces, the forces in the nucleus of atoms, which we call the strong and weak force. And the details of how the nuclear forces actually worked took many decades to work out properly, and was not really fully understood, I'd say, until the 70s. And so there was a 50-year hiatus between the 20s and the 70s. But by the 70s, there were new theories of gravity, that is to say, attempts to quantize gravity. That was always an issue from the beginning, because we had quantum mechanics, which by the 20s was well developed, and the other forces seemed to obey the rules of quantum mechanics. So the issue was, well, why couldn't we bring Einstein's theory of gravity into the quantum mechanical picture of things? And there were many attempts and many failures, but by the 70s there was a new theory that seemed to provide a way of doing this. This is called string theory. And the interesting thing about string theory is that it requires a hyperspace. It requires space to be space-time, that is, to be 10-dimensional. And suddenly people remembered, in the 70s, remembered these old Kaluza and Klein papers and we're using them to justify their approach to there being more than 4 dimensions of space-time. I have a book, for instance, called Modern Kaluza-Klein Theory, which is all about these new theories from the 70s and 80s. And so, people who had read Abbott's book, actually Abbott's book was republished, and many books came out referring to Abbott's book. So in a way, this old book from the early part of the 20th century had a new life of its own to help people, understand the idea of the hyperspaces that the physicists were talking about starting in the 70s, and now, there's no way of doing string theory without a hyperdimensional space-time. And of course, a lot of the work in string theory is in describing what the extra dimensions are like, what characterizes them. And there are many very interesting developments along that line. If you want me to talk about that, I can talk about that. But
that would be very interesting. But let me just ask a few questions at this point. Is the proposition that Klein made that these dimensions are as tiny as a Planck length, is that generally the accepted view now?
Well, it has to be, because we obviously don't see these extra dimensions that string theorists are talking about. So yeah, they have a word for it. They say the extra dimensions are compactified dimensions. Compact in the sense it's like a surface of a sphere or a torus would be compact. In other words, not spread out. And so, yeah, they think of the extra dimensions as being not much bigger than, say, 100 times bigger than the Planck length. Yes, that's the standard view in string theory.
But there might be other reasons that we don't experience them. Normally, they might be, for example, only approachable through consciousness, and then they might be vast in a certain way.
Yes, and among string theorists, there are also other versions of the theory that talk about the fact that space-time itself might be a 3 or 4 dimensional structure that's in effect swimming in a hyperdimensional space. That would be a very different picture. In that picture, the higher dimensions would be like a sea, and we're just a bubble in the sea. That would be a different picture. And there are string theorists working on that angle. Every angle that people can think of, they're working on to try to understand these. How there could be extra dimensions.
And I have one more question. With regard to the Planck length, that is a physical limit based on quantum theory, but as a mathematician, it would seem to me possible that you can mathematically work with any length. It could be infinitesimally smaller than the Planck length. Isn't that correct? You're not constrained.
Pardon?
You're not constrained as a mathematician the way the physicists are.
That's true. But the thing is that the Planck's. Let me mention something about Planck. The Planck length is named for Max Planck, who in 1900 in effect originated quantum theory with his famous equation E equals h times the frequency. In other words, the energy is equal to a certain number, which we call Planck, the Planck's constant, h, we usually call it, times the frequency of the thing. Like, in other words, this was applied originally to electromagnetism. You could think of the energy of an electromagnetic wave being related to its frequency by way of this constant, Planck's constant. But it turned out that Planck's constant is used all over the place in quantum mechanics. For instance, in Heisenberg's uncertainty principle, you get Planck's constant playing a role. It plays the fundamental role, in a sense, in quantum mechanics. Mm-hmm. And Jeffrey, you're right that in mathematics we can deal with distances of any size, and of course in physics we can deal with other quantities that aren't restricted by the Planck length. It's only distance mm-hmm. that is limited to the Planck length.
And I'm thinking specifically, Saul-Paul, of consciousness itself. If we're talking about like a spiritual realm, an afterlife, or a realm of archetypes or something, physical length might be immaterial. That you could have vast spiritual realms inside of an infinitesimally small physical dimension, couldn't you?
Yes. People have, I suppose, speculated about such things over the years, there are other aspects of string theory and physics in general that are perhaps related to what you're suggesting. Is that in string theory itself, it's very interesting that we picture a string as a one-dimensional thing, right? The string idea took the place of what we call point particles. Now, a point mm-hmm. doesn't have any size, and one of the problems with physics, fundamental physics before string theory, is that the fundamental particles, like electrons, are considered points. Now, that's an example of what you were talking about. Yeah. It doesn't have, that's infinitesimal. Okay.
Not constrained by the Planck length.
Not constrained by the Planck length. Yeah, the electron, mm-hmm. the size of the electron, and other fundamental particles like quarks, say. Mm-hmm. And that was actually a problem because it creates infinities that have to be gotten rid of by certain mathematical tricks that physicists do that mathematicians don't like. But mm-hmm. I won't go into that. But that's a big part of the story.
Yeah.
What we call quantum field theory.
Mm-hmm.
Now, string theory gets rid of that problem in one stroke by saying, the fundamental things aren't points; they're strings. They're line. They're one-dimensional objects.
Mm-hmm.
Okay. Now, the one-dimensional objects are doing things. They're spinning and they're vibrating and so on, and they're also interacting.
A one-dimensional object has length, doesn't it?
Length only, yeah.
Yeah. Mm-hmm.
Yeah. These strings have more characteristics than simply length. As I said, they're vibrating, and in fact, they're spinning at the speed of light. They're doing a lot of things, but more in a way more interesting than that is that they're interacting with other strings.
Mm-hmm.
They're meeting and joining and splitting, which is how they interact with other strings. And as they do this, they're sweeping out what we call a world sheet in space-time. Now, in quantum field theory, like in Feynman diagrams of quantum field theory, the particles that are point particles are sweeping out what we call world lines, okay, as they move. They sweep out world lines, and as they interact with other particles, they're sweeping out world lines. Well, in the case of strings, they're sweeping out world sheets, okay?
Yeah, membranes in effect.
It's a two-dimensional structure, okay?
Yeah.
And it itself is vibrating because the strings are vibrating, and it's vibrating in a 10-dimensional space.
Mm-hmm.
But the thing I wanted to point out that's very interesting is that this string theory sheet, world sheet, has to obey all kinds of constraints, like special relativity. Nothing can happen faster than the speed of light. But the more interesting than that is the fact that they have to obey something that we call conformal invariance. What that means is that size doesn't matter. Okay, I'm saying all this because of your suggestion that in the spiritual realm, maybe size doesn't matter. Well, I would say it's also true in a certain very fundamental aspect of the quantum realm, of the string theory realm, which is quantum mechanical, by the way. That's quantum mechanical constraints are other constraints that everything has to obey in this theory.
But the implications of the fact that size doesn't matter, I would think, are pretty enormous, because generally in quantum theory, the Planck length is an absolute limit. Yes.
Conformal invariance is across the board, and what does matter if size doesn't matter? Well, what matters is direction. By the way, a conformal transformation of a space. Size is not obeyed, but direction is. A perfect example of that we're very familiar with is the Mercator projection of the globe of the Earth. That is actually a conformal mapping of the globe, and what makes it valuable is the fact that direction is preserved, even though distance is. And we remark on the fact that distances are stretched, going north and go towards the North Pole, and going south towards the South Pole. They're stretched enormously. I mean, the North Pole actually becomes a line, stretching out the whole distance of the map. But it's a valuable map because direction is preserved. So navigators used it all the time in crossing the Atlantic, because it didn't matter so much about what mattered was the distance, was the direction you were going. If you kept going in the right direction, you would eventually get there, even though it might take a lot longer than the map might. Well, the map might actually suggest that it's take longer.
Right. You're talking about the maps where, of course, Alaska looks really much larger than it actually is because it's so far north.
Yeah, and Greenland looks bigger than South America, for instance.
Yeah,
which is a distortion, totally.
Yeah, but now coming back to the mathematics of all of this, we've talked quite a bit about your work with ADEX theory and the Coxeter diagrams, but I'm under the impression, in a general sense, that this type of mathematics is very useful for looking at when you have complex systems of many dimensions and many variables, how you can change one variable and keep other variables constant, or vice versa, change many variables and keep some constant, and the kinds of transformations that can occur.
Well, yeah, it's actually a bigger transformation than just fiddling with variables. I mean, what you're talking about, we do in ordinary algebra, actually. But what the Coxeter graphs allow one to do is to transform from one type of mathematical object to a very different type of mathematical object. For instance, you could go from what we call a catastrophe structure to something very different, conformal structure, let's say, two-dimensional. I mentioned that the two-dimensional conformal space of the world sheet. Remember? Mm-hmm. Well, two-dimensional conformal structures are ADE classified. Isn't that wild? So there's one of these structures for every and there are an infinite number of A's and an infinite number of D's, and as I've mentioned before, there are three, and this is very strange and interesting and beautiful. There are only three E's: E6, E7, and E8, which makes those dimensions very special, by the way. One way that the eighth dimension is automatically special in string theory is that I said that the two-dimensional world sheet is vibrating in a 10-dimensional space. But here's the thing: because it has to obey special relativity. Only 8 of those dimensions are actually active. In other words, what we call the transverse dimensions, going up and down, like a drum head. Moving a drum head is a two-dimensional space that's vibrating up and down, not vibrating very much side to side. So that would be an example of what I'm talking about. But in this case, we have a 10-dimensional drum head in effect. That's vibrating in 8 dimensionals up and down, transverse, we call them, and the E8 of the Coxeter graphs play a big role in that 8-dimensional situation.
Now, for purposes of clarity, let me be clear. Ask you this: do the dimensions themselves vibrate, or is it only the sheet or membrane or strings within the dimensions that are vibrating?
Yeah, the dimensions themselves don't vibrate. It's anything that's active in them, like this world sheet we're talking about. Yeah.
And these dimensions, even though they are not accessible to our normal sensory mechanisms, are actually thought of as spatial dimensions.
Yeah, well, one of them always has to be a time dimension. When we say 10 dimensions, it's 9 spatial dimensions and 1 time dimension. Yes. Yeah, these are dimensions of space-time we're talking about always. There are other dimensions involved, but they're mathematical dimensions of things that are different from space-time dimensions, and they're important too. But here we're talking about space-time dimensions. Yes.
Because if they weren't space-time dimensions, we'd probably just call them parameters rather than dimensions.
Well, in mathematics, we can call them dimensions or parameters, depending on the usage that we're familiar with or using at the time.
Okay. You were going to go into some of the other characteristics of these dimensions.
One type of structure that's ADE classified, which is a very interesting thing, and that's called catastrophe structures. Now, what we mean by catastrophe structure it's a dynamic system that can change drastically due to an almost infinitesimal change. Here's, I'm going to use the word parameter. In the parameters that are affecting the system. Okay, if a tiny change can create a big change in a dynamic system, the general term for that in mathematics is catastrophe.
This is where we get the metaphor of a butterfly flapping its wings in China can cause a hurricane in the Caribbean?
That would be an example of a tiny effect, a tiny parameter creating a huge effect. Yeah. Yeah, it's called the butterfly effect sometimes. But anyway, yeah, that would be such a case. But the thing is that the parameters that these catastrophe systems depend on are the parameters themselves are characterized by the Coxeter graphs. Actually, the nodes in the Coxeter graphs, it turns out, in this interpretation of the Coxeter graphs, actually encode the parameters that we're talking about, the parameters that affect the dynamic system. Actually, I have pictures of this in the paper that you published, and I show pictures of these of one case, one very simple example called A3. It relates to the A3 Coxeter graph, which is simply three nodes with lines attached between them. That's the Coxeter graph. But those three nodes are in the catastrophe interpretation of the graph. They're doing something quite interesting. It would take a while to go into the details, so we probably should talk about.
Maybe you could just summarize it quickly. Or is that not possible?
Well, yeah. Well, it has to do with the mirrors. Interestingly, remember that each of the nodes in Coxeter's theory correspond to a mirror that moves everything from one side of the mirror plane to the other side of the mirror plane. And the mirrors also create what we call virtual mirrors, as happens in the ordinary kaleidoscope. You start with two mirrors set at 60 degrees, and you get a virtual mirror, a third mirror, and that three mirror set then creates a snowflake pattern in the kaleidoscope of that type. And a really interesting thing about kaleidoscopes is that if you put an extra mirror in other words, you have it. I have several kaleidoscopes like that. You create a you just put a third mirror in, physical mirror in, connecting the other two mirrors. You create a triangle, right?
Yeah.
The light source is at the end, yeah. And what happens is beautiful. What happens is that the snowflake design spreads out effectively to infinity. Okay. It enlarges. It's not just confined to that little circle. It's the implication is that it spreads out. Okay.
So that's the difference between a real mirror and a virtual mirror.
Yeah, this is right. Right. The virtual mirror is a third mirror that is created by the two real mirrors. But in this case, putting in a real mirror. By the way, that's called when you do that, it creates what's called a Coxeter chamber, because he wrote about all this stuff long ago. And what that does algebraically, Coxeter was dealing with the problem of crystallography in hyperdimensional space. He was interested in answering the question of how could we characterize all possible crystallographic structures in dimensions of any number.
Earlier, you mentioned that there was a hiatus after the initial Kaluza-Klein five-dimensional theory for about 50 years before physicists became interested again in hyperspace. But when Coxeter was doing his work in the 1930s, this was during that hiatus. So mathematicians kept moving forward even though the physicists seemed to have dropped interest. Is that right?
Well, mathematicians have always been interested in mathematical hyperspace, spaces of any number of dimensions. Anything that they're dealing with, there's going to be some mathematician who's interested in, well, what does it look like in a bigger space? I mean, that's a mathematical problem. They don't have to worry about what the physicists think about it or not think about it. It was a big surprise when Coxeter's work was related to other work related to the catastrophe structures by V.I. Arnold. V.I. Arnold, a Russian mathematician who showed that catastrophe structures are ADE classified. Now, Arnold is a very interesting mathematician in the sense that he was also something of a physicist. He was very interested in physical dynamic systems. Not just mathematical dynamic systems, but being a mathematician, he was also interested in, well, what do hyperdimensional dynamic systems look like, and he classified them by way of the Coxeter graphs. But what I was going to say is that what these, when you put in this extra mirror and create an infinity. Actually, you create an infinity of mirrors, and therefore infinity of virtual mirrors. You see,
yeah,
and the Coxeter graphs classify something called Coxeter groups, which are called reflection groups because they have to do with reflections in mirrors. And when you create this Coxeter chamber by putting in an extra mirror, then what that does is it generalizes the reflection group to be an infinite reflection group. In other words, you start out with a finite number of elements in the Coxeter group, and then you wind up with an infinite number of elements. And both of these, all of this is related to how the catastrophe structures work, but it's hard to describe without pictures, I must say.
And obviously it's very complex because you're dealing in, as you say, a 10-dimensional space.
Yeah, you could be.
And so part of the work of the mathematics, the crystallographic structure of hyperspace, I suppose, has to do with things like the hyperspace angular relationships between these dimensions.
Yeah, well, one thing I should make clear right away is that when we talk about dimensions and talk about the bases of the dimensions, like we think of three-dimensional space as having a basis of, we usually use X, Y, and Z axes, for instance.
Right.
And these axes are set at 90 degrees to each other, right?
Right.
But that's not a mathematical requirement. If you're describing a space, the basis structure can be as long as the bases are what we call independent, then they can play the role that the XYZ axes do. For instance, you can have on a two-dimensional plane, you can have basis vectors set at 120 degrees from each other. Okay, and that would be a perfectly good system. It will be an angular, as I think you used the word angular. It would be an angular system, but it's very useful actually in mathematics. And typically in Coxeter's crystallographic spaces, the basis vectors are at 120 degrees. They're not at right angles. In fact, something that's at right angle is going to be separate from his structures. A right angle, in effect, doesn't create a barrier, but a separation, in effect.
Now, the fact that there are these basis vectors suggests to me that the hyperspatial dimensions do intersect with each other.
Oh yeah, for sure. Well, yeah, they do intersect. Otherwise, there wouldn't be any point in having such a system. Yeah, yeah, they intersect. Sure, absolutely.
But the fact that they're hypothesized to be so tiny, I think, would mean that the intersection has to occur in a very precise location, or maybe I'm misconstruing it completely.
Well, precision is part of the mathematical picture of what's going on. One way of thinking about this is that these dimensions are all inside us. I mean, because they're tiny, they're all inside everything. They're inside us. One could quote Jesus and say the kingdom of God is within you. Okay, not that he knew anything about hyperspace necessarily.
Well, here's where I'm having trouble picturing this. If the dimensions are so tiny, like you say 100 times a Planck length or something very, very small like that. So, and if they're inside of me, does that mean if it's inside of my right hand, it cannot be inside of my left hand because my left hand is too far away? Or is it that even though they're very tiny, I can access them from possibly any point within my body?
Oh, yeah, for sure. Yeah, they're right.
They're not like tiny bubbles.
No. Well, there are bubble type dimensions, and it could be toroidal dimensions. I mean, some in some versions of the hyperspace, the hyperdimensions are like hypertoruses. They're like in a 10-dimensional space, you would have a 6-dimensional torus. Say a torus is a mathematical term for what we call a donut-shaped thing. It's mathematically simply a product of two circles. In a donut, one circle would be going around one way, and the other circle going around the other way, right? but mathematically, you can have any number of circles that are, we say, multiplying each other, and so you could have an n-dimensional torus, a product of n circles, we'd say, and this isn't a product like multiplying two numbers together. What we mean by product is actually that the size, in effect, is multiplied. The area, or larger versions of area, right?
It sort of reminds me of Ezekiel's vision of wheels within wheels. It's like we're getting into an area that just defies human language because it's so different from things that we normally experience in a 3D space.
Well, that's why we use mathematical language. Without the mathematical language and structures, we wouldn't be able to think about it. Yeah, for sure.
You know, Saul-Paul, I remember back in the day when you and I were living together at the Institute for the Study of Consciousness with Arthur Young. Arthur was involved in the publication of an anthology, a paperback that was quite popular at the time called Consciousness and Reality. And if I remember correctly, there was an article in there written by his co-editor, Charles Muzes, about some mathematicians seem to have the unique, uncanny ability to actually visualize and see clearly in their mind these hyperspace objects.
Well, yeah, an interesting thing about that, Jeffrey, is that what Charles Muzes was publishing in this book, Consciousness and Reality. As you say, it was an anthology of papers. But one of the papers that he put together was actually excerpts from Coxeter's book on regular polytopes, which is about crystallographic structures, And yeah, Coxeter in that book describes three different people, very different people, all of whom seem to have the ability to visualize four-dimensional space, visualize in some sense, to be able to describe what's going on in such a space. And one of them was the daughter of the famous mathematician Boole. You may have heard of Boolean algebra, which is used as a basis, in a sense, of computers.
If then else, isn't that Boolean logic?
Boolean logic, yeah. Anyway, one of his daughters was able to visualize four-dimensional space and actually worked with Coxeter in helping him. He couldn't visualize four-dimensional space, but she could. And when he was trying to work out four-dimensional structures, she aided him. Actually, they worked together on visualize. She could visualize, he couldn't. But anyway, that she's perhaps the most interesting case. But there were two others who one of them was an Armenian carpet, Middle Eastern carpet not salesman. He ran a company, I guess, importing carpets, and these carpets have very interesting abstract designs, and maybe his ability to visualize four-dimensional space helped him in that business. I don't know, but I forget what the third person was, but he described three of them, and as you say, Muzes published this in Consciousness and Reality. All of this goes back to the interest in four dimensions and higher dimensional spaces, going back to Abbott. Also, a very interesting thing about four-dimensional space is that Coxeter pointed out that there's a certain structure in four-dimensional space that has 24 vertices, and it's self-dual. So it's very beautiful from a mathematical point of view. Self-dual in the same way that a cube and an octahedron are self-dual.
What does that mean, self-dual?
It means that the vertices of one diagram correspond to the faces of the other. Now, in this case, we're talking about three-dimensional faces because it's a four-dimensional object, right? A three-dimensional object has two-dimensional faces, yep, or facets. Anyway, so the duality has to do with the vertices of one object corresponding exactly to the faces of the other object. And for instance, if you put a point in the center of each of the faces, that becomes the vertices of the dual diagram, of the dual figure. And so this is, he calls it a 24 cell, by the way, because there are 24 three-dimensional faces. And he points out that there's no analog for the 24 cell in either higher dimensional spaces or lower dimensional spaces. So it's unique. And there are other ways that mathematicians have discovered that four-dimensional space is very special, by the way, but that's a whole other topic. And physicists are very interested in four-dimensional space as space-time, but mathematicians are interested in four-dimensional spaces for very different reasons from the physicists' space-time thing. I sympathize with the fact that people find thinking about hyperspace is very difficult because we simply don't have any experience.
Except for these gifted people, it's almost like a psychic gift, clairvoyance, or maybe it's closer to synesthesia. But some people's brains seem to be wired in a way that it's natural for them.
Yeah, and there was a guy named Hinton, who a mathematician named Hinton, who was actually the teacher of this daughter of Boole's, who developed a way of trying to teach people to visualize four-dimensional space, but it was very very difficult, and very few people were able to do it. And this daughter of Boole's was able to do it, and she could do it better than Hinton himself could do it.
Yeah.
So that's very interesting. Yeah, there's an interesting book by Rudy Rucker called The Fourth Dimension, where he goes into all this in great detail. A very readable book if people are interested in hyperspace. And he also talks about the possible relationship of this to more far out things like the paranormal and so on. But as soon as Abbott's book came out, people tried to apply Abbott's ideas to the paranormal. Of course, that was a big topic.
In fact, it's very interesting because I recall reading a biography of B.F. Skinner, the famous behavioral psychologist, and he says in his youth he was fascinated by Flatland and thought that it might offer a way to understand human consciousness. Then he says he realized that was infantile thinking, and he moved on to behaviorism. Yeah.
Well, fortunately, I think that psychology has moved beyond behaviorism.
Thankfully.
For the most part,
Yeah.
although I'm sure there are plenty of strong behaviorists still around. But
Yeah.
Skinner's ideas have been surpassed by better methods and better ideas. But I think behaviorism still affects us, though, psychologically, because it was a strong movement for so long.
Yes, it dominated psychology for 50 years. It suppressed the study of consciousness, but I guess one can say that psychology went in that direction because it seemed to give them a better use of the scientific method, a better handle on how to integrate the study of the mind with the scientific methods that existed at that time.
Yes. Yeah, you could do experiments with good controls and all that.
Yeah.
Mm-hmm.
Well, Saul-Paul, we've been going for about an hour, and probably many of our viewers are having a hard time digesting a lot more, and I'm sure there's much more to say about hyperspace, but I think at this point we'll work it into some of our future conversations.
Yes, let's do that.
So once again, let me thank you for being with me and thank our audience for being with us.
Thank you, Jeffrey. It's fun.
It's been a pleasure, and I look forward to more conversations with you.